Thank you very much. So first of all, I would like to thank the organizer for giving me the opportunity to talk and the ICTS for hosting this workshop. So it's a very recent work I did at Northumbria. So it's also in Newcastle, but it's the other university. And usually I'm more a one-dimensional guy, so more non-linear waves, but it's very recent, so now I start looking at 2D in non-linear system. And it's a work I did in collaboration with Nicolas Pavlov from Université Paris-Saclay, and Pierre Azam and Romain Kaiser in Université Côte d'Azur in Nice. Okay, so I start right away with what we were looking at. So it started with an experiment that has been done by Pierre and Romain in Nice. And it's the following system. We have a laser beam that propagates inside a Kerr-type medium. So here it's atomic vapor. But what is important is the effect of the atomic vapor on the electric field. And if you do the paraxial approximation, so here I'm separating the electric field into an envelope and a carrier wave, you can write a nonlinear Schrödinger equation. So I'm using this terminology, nonlinear Schrödinger equation or Gross-Pitayevsky equation for me are the same here. So what is important here is what is the role of the coordinates. So there is no time variable. Here it's kind of stationary. What plays the role of time for us is the z-axis. So as you propagate along the z-axis, so here there are different snapshots of the experiment. It's as if we are taking different snapshots in time. And we're in 2 dimensions. So what plays the 2 dimension here is the plane orthogonal to z, so x and y. And so that's the NLS equation here. So I will skip the explanation of the coefficients. In this kind of system, we cannot get rid of the absorption. So here you have an absorbing term. But in the kind of qualitative description that I will do here, it does not play an important role. And so that's the experiment. And in this experiment, we start with this kind of profile. So here you're looking at the intensity of the light at z equals 0, so at the entry of the cell. And you have some kind of Gaussian pattern, and you create a hole inside. So that's what you start with. There is also a phase pattern. I will show it after. But let's first focus on this intensity pattern. So the Gross-Pitayevsky equation, or the focusing NLS. So what's happening to this kind of dip? So here I will show you a numeric that reproduces the experiment, that you have a dip that is quite unidimensional, actually. And what it will do is that it will generate depletion wave, it will generate soliton that will propagate both up, so along the y-axis, and down. So that's, and I would like to stop it at some point. So that's what you see here. So on the right, there is a phase pattern, but let's forget it for now. I will talk about it later. And okay, maybe I should have zoomed in here. But if you look closely, you see that you have some gray solitons that are propagating up and gray solitons that are propagating down. In defocusing NLS, so when you have this repulsive interaction, it's not a stable structure in 2 dimensions. The dark soliton, it knows to have this transverse instability that is also called snake instability. And what it will do, it will, oops. So let's play it again. The dark soliton will basically decay into a pair of vortices. So that's what you can start to observe here. I should have accelerated a little bit. But you can start the generation of soliton. And if you look here closely, you have this phase jump of 2 pi between two vortices. Okay, so that's a video. And so Pierre and Robin made this experiment with different type of initial condition. and looked at the end of the cell at the different patterns. So here it's different initial condition, and on the right it's the numerics. So it's quite a good agreement here. Why are we also looking at numerics here? Because in the experiment we can only record what's happening at the end of the cell. You cannot see what's happening in between. So we'll be using some numerics to see how we end up with this pattern, basically. So what was really nice with this experiment is that beside recording the intensity of the light, you can also record the phase of the electric field. And it gives you some information. So for us here, once again, you write psi as an amplitude, or if you want an intensity field, and the phase. And if you compute the gradient of the phase, you have the velocity, your velocity field. So that's the thing we can also record in this experiment. So what I will draw, and I think most of my slides are always this kind of plots. I will draw the streamlines to represent the variation of the vector field. So basically, it's just the integration of this ODE. So at any point of your 2D plane here, you have the direction of the vector field. And the thing that we were interested in is, of course, the formation of the vortices here. But as you can see in the middle here, you have a saddle. The saddle, it's not a singularity, it's an equilibrium point. So here the velocity is equal to 0. And we wanted to understand here why we have a saddle here, how does it appear in the mechanism of creation of vortices. And it's something quite ubiquitous in quantum fluids. So here so it's not, it's coming from this different paper. And you can see here we have different experiments. So BEC in 2D BEC, so you have formation of vortices, and you can notice here that you have also some saddles. The same in polariton. So here in the Leche groups, I think we have many authors of this paper in the audience. Actually, the same. You have the creation of saddles at the same time as the vortices. And also in nonlinear light, so something quite similar to what I've just shown. You have also here, between these two vortices, you have a saddle. And so that's the thing we wanted to understand. And okay, before I go to this slide, that's something that Nicolas have been working on a little bit before. Why do we have saddles at the same time as vortices? So first, I would like just to start with this toy model. So you have a field psi. It's not solution to any peculiar equation, but what you are just writing here, you're writing a vortex solution that is embedded into some flow. So here, along the x-axis. And what you observe here, you observe the streamline, you observe a vortex, and suddenly a saddle. So it's something that comes naturally. As soon as you embed a vortex in a flow, you will have the creation of a saddle. So here I'm just showing this picture just to introduce another type of line. This line here in multiple color are line of equal phase. So I will reuse this line later on. And now the idea is that, okay, you have a vortex in a flow, it creates a saddle. So now how a vortex and an anti-vortex in a flow would interact. So that's the following slide. So it's a work that's been done by Nye and his collaborator in Bristol in '88. And the question was the following: to find the solution of the stationary wave equation in 2 dimensions, and to see what's happening if you try to make these two vortices interact. So in that case, when B, so they found this solution. When B is very large, you can really see it as just the superposition of the two solutions I showed before, except that now you have one vortex in the trigonometric direction and one in the clockwise direction. So when B is large, they are separated, they are not interacting if you want. And as you decrease B, you have this kind of nice I would say, a trajectory of the saddle that actually in the papers they call it the dance of saddles. What's happening is that first the saddles, they get closer, they create this kind of new structure that separate again into two saddles, and ultimately the two saddles dies with the vortex and the anti-vortex. Okay, so that was the idea here, and it's just the solution of this linear equation. Actually, this provides kind of an explanation of what we call amphidromic points and how they are created. Actually, I realize that I'm also putting a picture of UK I can do. So I don't know, maybe Newcastle we like to do this kind of picture. So you have UK here, you have the North Sea, and what are amphidromic points? Basically this point there, where the lines are called co-tidal line. So basically, it's all the point when it is simultaneously high tide. So here at a certain hour, that will be the high tide will be in this region, then here, etc. And of course, so this is, if you want a wave, and as it propagates, it will create some flow. And if you take the perpendicular line here to the co-tidal line, you will get some kind of vortices, if you want. And the nice thing is that between two amphidromic points, you can notice here a saddle. So it's hard on this picture to see the saddle. It's easier to see it here. But that's the idea, is that similarly to quantum fluid here, you can also notice, as soon as you have a vortice, some vortices, you also have some saddles. And it provides some nice explanation of how the tidal line behave when you are close to amphidromic points. So that's, we are no longer in the North Sea, now it's close to the South America coast. Here you have Brazil. And you have your co-tidal line here without any vortices. And so here there is no really parameter that we can vary, like I showed in the previous picture, where you had this parameter B that you can change. So here, it's actually more complicated than that. It's neither really a solution of the stationary wave equation. It's really a toy model here. But it happens that sometimes two amphidromic points appear here, and they appear with their saddle. And that was something that was surprising at the beginning, because when they measure the tide there, it's not having it was not having the expected behavior, because people were thinking that there won't be saddles, but no, it's okay. You have saddle here. So here I'm just putting again the picture I showed you before. So the co-tidal line were all line of equal phase, and now perpendicular to the line of equal phase, you have the flow. Okay, so that was for this stationary wave equation. And once again, here it's kind of a toy model for these amphidromic points. But Nicolas also looked at this kind of problem for 2D scattering on a cylindrical obstacle. So here it's still linear equation, if you want Schrödinger equation, where U here is this cylindrical potential, so drawn here. And now you have the streamline there. And you have a solution for this. It is parameterized. The solution, you have an incident wave, and it's parameterized with its wave number k. And as you increase k, you reproduce exactly the same dance of saddles. So first, you have these vortices with their own saddles, because they are embedded into some flow. And as you increase k, they will get closer, start interacting with this complicated pattern, and disappear. So sorry, I forgot to precise the work by Nicolas and Anatoly Kamchatner. Okay, and so at that point, when we were seeing this experiments done by Pierre and Robin, we were wondering, okay, is it the same kind of pattern? We have saddles at the end of the mechanism, so probably would be the same. Oh, before I talk, sorry, I forgot to talk about this important thing. So in this mechanism of creation of saddle and vortices, you have two indices that are conserved. There is one that is quite known, it's the vorticity. So basically, you draw a contour and you integrate on this contour the circulation of the velocity field. Basically, it's just integrating. If you have the velocity field is a gradient of some phase, you're just integrating the phase over the contour. And by definition, it has to be 0 or a multiple of 2 pi. Okay, and here if you put a vortex or an anti-vortex, you get positive or a negative integer. There's actually another index that exists called the Poincaré-Hopf index. And it's independent actually from the nature of the velocity field. It can be a gradient or not. You will always have this index. And what it is, basically, it's the integration of the angle that the velocity field is making with, I don't know, let's say the x-axis. By definition, since your contour is closed here, you have to get back to the same orientation. So once you integrate this theta, here it can only be 0 or a multiple of 2 pi. So you have these two index. And if inside you put a vortex, you get these two things. For the vorticity +1 if it is a trigonometric sense, -1 if it is the other direction. The Poincaré index is 1. And actually, so if you are not familiar with this computation, here it's easy to see. You see that if you look at the arrow of the velocity field, basically you're just doing a rotation of 2 pi. And you can convince yourself, I mean, if you rotate in the other direction, you will also get 1. For the saddle, it's not the case. For the saddle, the vorticity, of course, is equal to 0. But if you look at the vector field, when you follow the contour here, you see that the vector field is actually rotating in the clockwise direction. And because of this, you get a Poincaré index of -1. So now, when you play this game of continuously deforming your vector field, like we are doing in this game of dense of saddle, these two charges, these two indices should be conserved. And that's the case. So let's just check. So here I took three pictures, and I started when we had this kind of weird critical point that actually has vorticity equal to 0, but a Poincaré index of -2. And you have your two vortex, one with vorticity -1, the other one with 1, but with Poincaré index equal to 1 for both. And as you can see, here our structure with -2 for the Poincaré index separated into two saddles. It's conserved locally. You have -1 plus -1. And then when they all annihilate together, so here it's just simple addition of indices, you get 0, 0. And here it's normal because you don't have any critical points. So somehow, this conservation of these two indices show you that here you need to have this saddle to have the annihilation of vortex. The vortex cannot annihilate together just to give this flow. You need these two saddles to cancel the Poincaré index of the vortex. Okay, and we thought that it would be the same for the experiment when we were discussing with Pierre and Robin. We were looking at the numerics, but we are not really paying attention first at the velocity field. We are thinking, okay, we have this creation of pair of vortices. What we should be observing there and there is saddles. And it was not the case, actually. We are not observing any creation of saddles when the two vortices were forming. And actually, what's happening is that if you look just before the creation of the vortices, so here the snake instability, so as the initial curvature of your dark soliton increases, so it increases more and more. That's where you start having the creation of these two vortices. And if you wait sufficiently long, then the soliton breaks totally and you have these two vortices. But what's happening is that before you have this formation of closed orbit here, you have two extrema of the phase. So here you have a minima and here you have a maxima. So let's just do a zoom in here. If you have an extremum of the phase, the streamlines look like this. So here it's for a minimum, for a maximum, the arrow will be in the other direction. And same as the saddle, it's an equilibrium point. So here the velocity field is equal to 0 at these 2 points. But what is nice now is that from the point of view of the topological index here, we can have these two vortices alone. Why? Because here they don't carry any vorticity. So you go from 0 plus 0 equal minus 1 to 1. But they have a Poincaré index here. You have 1 plus 1 equal 1 plus 1. And once again, here the Poincaré index is very easy to compute. You see that if you look at the orientation of the velocity field and you do a 2 pi rotation, you have just 2 pi. So we were quite surprised, especially because it was not really observed before. And there was a reason why. So the model I showed before, the one described by the Bristol group, they were looking at a stationary wave equation, and you can show quite easily that you cannot have any extremum of the phase. Sometimes the other place where it was looked at, it was an incompressible fluid, and in incompressible fluid, because the divergence of the velocity, or if you want the Laplacian of S is equal to 0, you cannot have this extrema of the phase. That was one reason why it was not observed before. Okay. Oops, sorry. So that's what we had. And actually, if you take another point of view for this kind of pattern, it's not surprising that we have these two kind of mechanisms, either with saddle or with knot. So for this, I will do, in the remaining time here, I see that I'm a little bit out of time, but I will go quickly. We'll adopt another point of view, which is a dynamical system point of view. So here, as I told you, when we draw these streamlines, basically we are integrating this ODE. This ODE basically defines a two-dimensional dynamical system. It's autonomous, since the vector field only depends on the position. And there is a well-known theory of how saddles, nodes are created when you vary continuously a parameter. It's the bifurcation theory. So here is just a small example. That's not something that I showed you with the experiment, but that's something you can observe actually. If you take this kind of vector field, you have a parameter, one parameter A. There is no equilibria, and as you increase it, you create here a node, a minimum of the phase, and a saddle. And in that case, it's conserved. The Poincaré index is conserved. You have 1 plus minus 1 equals 0. Actually, here, the vorticity is also conserved because it's very easy to write this vector field as a gradient of a phase. So the vorticity is also conserved in that case. And for those who are kind of more in the dynamical system realm here, so it's codimension 1 because I'm only varying one parameter. And what we observed here, so the two kind of mechanism I was talking about actually appear in a very in a well-known kind of bifurcation. It's called the fold-up bifurcation. So here you open any book on bifurcation theory, and in the list of codimension 2 bifurcations that you have this one, where actually you have two parameters that you should vary. So here, I'm sorry, for those who are really familiar with a dynamical system, it's not exactly the normal form of the fold-up bifurcation, but okay, here is just to simplify the discussion. And in our case, here, this parameter A will be actually equal to 0, so we are looking at kind of a degenerate case of the fold-up bifurcation. But if I draw now the trajectory of this system, so sigma can be plus or minus 1, I'm reproducing exactly these two mechanisms of creation of vortices that we have seen, either with the saddle or with the knots. And okay, and here I will go quickly, but in the theory of dynamical system, as you can see, you don't have any singularities if you look for fixed point of this system. These are not vortices here. These are just, so we call them center, are just equilibrium surrounded by closed orbits. But what we have done with Nicolas, Pierre, and Robin, we found a system, gradient system, that is actually orbitally equivalent to this normal form of the fold-off bifurcation. So basically, we find the S, a phase that reproduce exactly the same orbit than this one. And here, sorry, I'm skipping a little bit the detail. That's what you end up with. You obtain with this phase profile for the one that has been observed by the Bristol group, and this phase profile for our experiment. And actually, it's quite interesting. If you take the solution of the Bristol group, you do a Taylor expansion for small x, small y, and small parameter b. So you look very close to the bifurcation point. You obtain exactly this phase. Okay, and here I have to wrap up. So I hope I convince you that you have kind of two mechanisms of vortices creation, and in both you need to look at this conservation of vorticity and Poincaré Hopf index. So they involve critical points that are different from vortices. So it's good candidate. It's good candidate for observable for studying the transition to turbulence. And okay, maybe this can help to understand the kinetic of the number of vortices, saddle, etc. And it's also, I mean, we're also thinking maybe I look at other nonlinear phenomena where this topological constraint can be important. So to wrap up here, so thank you.
Since we absorbed the coffee break for half an hour, so questions. Go. Do you have the mic?
Yeah, so I guess I'm struggling to sort of understand that. Do these saddles have a dynamically significant role like vortices? Because I mean, typically you can always, when you have a phase field, you decompose into maybe a contribution that's due to a compressible part and an incompressible divergence-free part. And the divergence-free part is really the dynamics are completely, completely determined by the point vortices. So I'm wondering, I mean, in that sense, do these saddles play a dynamically significant role?
It's a very good question. So is the saddle or the knot playing? So that's something that we're actually looking at with actually people from the group of Lecce. I mean, how all this kind of topological constraint or this mechanism kind of influence all this kind of kinetic of the creation of these vortices. But it's a good question indeed, because they don't have, the same, it's equilibrium point, it's not singularity like the vortices. So, yeah, that's something where...
I mean, if you go back to I think there's a figure, here. I mean, can I just ask, so if you take the top left figure, and you add a uniform background flow, okay, completely independent of position, just constant, would you get something that looks like the lower right figure? So in other words, the location of saddles depends on the frame of reference you're looking in.
I would say, you would multiply. It's a good question. I don't think so, because then you would be...
It's something.
It's a good question. The thing is, from the point of view of, if you add, it's a drastic change. Just amending it in another flow. So it's not something that you would really observe when you deform, when you slightly. In the end, what we are why are we talking about dynamical system here and bifurcation? Because when you do the dynamic, so along the z-axis, it's kind of a smooth dynamic. I mean, it's a kind of continuous deformation of, but it's a good question. Maybe if you do it drastically, you would probably, I mean, okay, it's an easy thing to check, but it will imply that you are doing a drastic change. You are imposing suddenly another flow to.
Thank you.
Are there any other quick questions? Otherwise, we sort of, merged it into the coffee break. Okay, so if not, let's thank Thibault again, and indeed Rahul and Andrew as well for the talks this morning.